most of you who are only watching or not able to attend, before I get to homework questions, the practice midterm and solution are available on the main page in Canvas. Here's a practice test. It covers material for section 7.4. This part of the first question deals with 7.4, so you've not seen it yet. You would not know how to do this yet, but you will after Tuesday. So this is from section 7.4. Sorry for repetition, everyone, because I forgot to start recording. There's a floating point arithmetic question from section 2.2. Problem about convergence is section 2.1. Lagrange interpolation, so this is section 7.2. So given a function, given interpolation points, write down the interpolating polynomial in Lagrange form. And this also deals with 7.4, estimating the error in the interpolant at a certain point. And then last question, what I covered earlier this week, Newton interpolation. So another interpolation problem, write the polynomial in Newton form. So that involves computing divided differences. And again, estimating the error at a point. And then, as I mentioned on Tuesday, there'll be concept check kind of questions that follow, 10 of them. So we're not included here, but you can look at the quizzes, get an idea of what sort of things will be asked about in that section. For the solution, so everything is written out here. Now, the thing I want to point out is when you get a problem like this one on the real test, I am not looking for this every single little detail. I'm being very detailed in here to help your understanding of how to work these problems. I do need you to show your work, of course, but I just want to make sure no one's getting having a misconception of about what's required. So it's not. And here I'm showing every little step. But as long as I can follow what you're doing and I can see, that you understand the material to obtain the result, that's what I'm looking for. Okay. So be sure to take a look at this for the October 12th class. That's a week from Tuesday. That class will be review, so be sure to look this over, see if you have any questions. That'd be a good time to bring those up. All right. Okay. So now, everyone here in the room or out there in WebEx land, the floor is yours.
One of the homework questions I had the most trouble with was 2.1.13.
2-1-13. Okay.
And mainly, I just didn't really know where to begin. I got,
Okay, so,
so you have the Taylor expansion, and you basically substitute it into the equation there, and then you subtract the remainder from it, and that's the error.
yeah, so, but yeah, so actually you do know where to begin.
Okay.
Whatever Taylor expansions are required are what you substitute. And the thing is, because when you write out the Taylor expansion up to a certain point and include a remainder term, so that is exactly equal to this. So you go ahead and substitute. And actually, there's one point that could be made a little clearer, and I will do that now, because this question came up from someone else earlier. So in both cases, you're dealing with an approximation of f prime of x naught. So after you substitute any Taylor expansions, write equation in this form. Because what will happen is, after you substitute the Taylor expansions in, one of them here, two of them here, and start simplifying things, then f prime of x naught will appear. So you're just working with this expression and and Taylor expansion will naturally introduce f prime of x naught. So f prime of x naught, you want isolated on one side, and then you'll have whatever the approximation is. So find a difference approximation. And then plus the error. That way, the error term will have a correct sign that matches what you see here. So the error term is defined under using this assumption. Next, if we go back to the example, okay. So you can see how it's being done here, that really what you're doing is you're forming this expression. And okay, actually, I'll go ahead and write this out too. Okay, so for example, the first part, this is your starting point. And this says equals something. Now, what does that equal to? Well, it's what you get by substituting your Taylor expansions into this. So after, so Taylor expansions, okay, what I mean by that is, okay, so another way of putting it is, you're gonna set this equal to minus f of x naught over h. So once you dump that in here, that's when a bunch of simplification will happen. F prime of x naught will appear. Certain terms will cancel out. The remainder term will appear. But then once you've done all that, then you want to rearrange it algebraically to get f prime by itself on one side. And then the error term that's stated in the problem should appear over here. All right. Any further questions from anybody on this one, or you can bring up another one? Yeah.
When you expand when you do the Taylor expansion of f x naught plus h, is x naught the radius?
X naught is the center.
The center, yeah.
Yeah. So you think of h as like being a radius.
Okay.
So we have a number of people in the Teams meeting. Any questions you have, you can type them into the chat or shout them out. Don't be shy. Or anything further in here. Got plenty of time.
I have a question about the expiration 2.2.22.
Okay. Okay. Okay, so this is one about, okay. Okay? Go ahead.
For the algebraic manipulation, is that just multiplying by the conjugate?
Yeah.
Okay, that's what I did, and I ended up getting still having a square root in the denominator. Um,
That's okay. The thing to keep in mind is, if you look at the original quadratic formula where you have these two possibilities, and if we, so the situation gets bad when the b squared is much larger than 4ac. So then this this square root works out to be approximately the absolute value of b. So one of these, either a choice of a plus or a minus, is a subtraction that will have a cancellation error. So, but that means that the other one is okay. So it's important to keep track of, and actually what I would suggest is, when you write out your original quadratic formula, just go with one of the choices, plus or minus. Carry out the manipulations and see what you get. And then also for the other case.
okay, yeah, that's kind of what I got. My final answer was if b is much greater than a and c, then use the new equation for x1 and the original for x2, and vice versa.
Yeah, either formula, the original quadratic or revised quadratic, will be fine for one root and not fine for the other. So at least for both roots, there's a good way to compute one of them, or there's what that you have a way to compute each root that's stable.
Okay, thank you. That helps.
All right. So a practical code for computing roots of a quadratic equation would have would not simply go ahead in the quadratic formula. It actually have an if statement that based on the sign of b in terms of which quadratic formula for which root. Okay, so we've got in the chat. Okay, 2219. Okay, this one. I expected a question on this one. Over the years, just given people fits. Okay, so the challenge for me is to put out a breadcrumb about giving something away or giving too much away. Okay, So okay, so since you have to find out how overflow can occur, well, so first I'm going to suggest an assumption, which really is one of those, as math professors often say, without loss of generality, but this makes it easier to discuss things. I'm going to have you assume that x is the larger of the two numbers in the sum of squares. So with that idea in mind, which operation in the original expression as written, so what you're doing here is you're squaring x, you're squaring y, you're adding them, and then taking the square root of that. So even though x and y and z are simply representing those numbers in the floating point system, none of those overflow. You're looking for an intermediate result. Okay. So that's the first question you should ask yourself. If you think of what's being done here, squaring, adding, taking a square root, what could lead to a number that's too big, even if x and y themselves are not too big? Then, once you have a handle on that, then the next thing to look into is how can you ensure that the offending operation, so the arithmetic operation that caused overflow, so whatever operation goes bad, you can perform that operation on a different number that's so that you can be certain won't overflow. For example, if you're dealing with a number that is known to be less than 1, maybe in a circumstance like that, you would end up not overflowing. Okay. Now, a key assumption we're making here is that z itself does not overflow. But because we have a square root of sum of squares, we have the following. Z is greater than or equal to absolute value of x, also greater than or equal to the absolute value of y. Okay. All right. So, again, I want to be careful to give guidance, but not excessive guidance. All right, I'll give us one last breadcrumb in this memory of how difficult a problem this can be. All right, that you can factor anything out of anything. Now, that sounds like a strange thing to say, but let me explain what I mean. Students get accustomed to factoring only in certain very limited situations that's not, it doesn't really cover situations where factoring is warranted. For example, if you can clearly recognize some common factor in whatever expression you're having, then yes, of course, you can factor it out. Or for instance, pulling a constant factor out of a derivative or integral, things like that. But there are times where it may not really be obvious that you can factor something out, but it's still a good idea to do so. And as long as you make sure everything works out correctly, that you factor something out and you compensate for it in what's left behind, you can do it. So if I have, and just to make a pretty ludicrous example here, this is just a total made-up expression. I have some expression a plus b, that if I want to factor something out that isn't even there, I'm allowed to do that. I can just put a c, factor out a c as long as I compensate for it. Alright, and because if that serves some purpose, if that makes things easier for me, then I should go ahead and do that. It seems kind of odd. It's something that a student is maybe not be used to, but this is the sort of thing that's called for. So, okay. So see what you can do with that. Alright, still both loads of time? Could be what the only calculation that's happening now for me or all of you is how long do we let silence persist before we decide class is over? One comment I want to make about one of the problems, there has been a question about it. This one right here, 2.2.7. Alright. One thing I want to make sure is clear, that, okay, you're given two numbers, so you're specifying parameters for one floating point system. The base is already specified. So your answer must consist of one value each of P, L, and U. So precision and the lower and upper bounds and exponents that will accommodate both given numbers. So you want to have enough precision to handle whatever digits are in these two numbers, and then a range of exponents that both these numbers will fit within. So sometimes I've gotten strange answers like someone specifying two different precisions, like one for each number. No, one P that is enough, is sufficient for both. And since your floating point system has a range of exponents, it takes at least two numbers to suggest a non-trivial range. Okay, two problems that were both assigned that are related to one another. 2 to 8, and then 2 to 11. Okay. In the first one, 2 and 8, numbers are not normalized. Near when they are. Because when a number is normalized, then it's assumed that the leading digit, one digit that's to the left of a decimal point, in the mantissa has to be non-zero. But in 2 to 8, it's explicitly told that you do not assume that. So numbers are not normalized.
For the last part of 228, the description you're looking for, is that just, our numbers should resemble certain notation we're very familiar with?
Okay, so all right, so this so since earlier problem you give us specific values for P, L, and U. For this part of the question, you're expressing these values in terms of general P, L, or U. And only the base is filled in.
Oh, okay.
Yeah. Yeah, and that's something I brought up when I was first covering overflow and underflow. I'm looking for viewer problem to see if it's based on past students and particular should be brought up. Okay, actually, this last one in section 25 is worth comment. All right. Now, you're asked which size X would cause cancellation error. Now, you not need to consider X for which the expression is undefined. So focus on values of X for which the expression certainly can be computed, and that it has a value. It's just that that value is difficult to compute accurately because there's a cancellation situation. Keep in mind when cancellation occurs. If you're subtracting two numbers, what is true of those two numbers that leads to cancellation error, and how will that come about? Like, what values of X will bring that situation about? Like, for example, here you can tell that if you plug in, X equals plus or minus 1, the expression is undefined. That's a whole other situation we're not dealing with here. So steer clear of that. So you can assume X not equal to plus or minus 1. So it's not of interest for this problem. whatever comes to mind. But using petition number as straightforward error, the way we work with petition number is that there's formulas for the absolute and relative petition numbers that use a derivative of a function under consideration. So that's what you should use for this problem. And since you're dealing with a specific point, that's the point of interest here. So, as far as the homeworks are concerned, in relation to the midterm, for example, for these two homeworks, okay, so this is chapter 2 homework. So these homeworks deal with chapter 7 that we're in the middle of now, polynomial interpolation. That's if you're taking advantage of the fact, and I know that a lot of people are, that I'm not actually enforcing homework due dates, and there's going to be a period of time in the schedule where there aren't any new due dates. There's a gap here that you can take advantage of. That, as I mentioned, that the midterm doesn't have MATLAB exercises on it. So if you want to, if you want to take a look at the chapter 7 homework as a way to help you prepare for the midterm, then you can focus on whatever problems that don't involve MATLAB. For example, there's a problem in section 7.4 that deals with interpolation error, and I'm going to cover on Tuesday. And as you saw, that comes up in a few different places on the midterms. And I'll talk about that in depth on Tuesday. So that would be a good problem to look at before the midterm. And for polynomial interpolation in general, you saw on the practice what are the things you should be able to do. Given a function and given some interpolation points, be able to come up with the interpolating polynomial of the correct degree in Lagrange form or Newton form. Be able to estimate the error. So those are the things that are essential from chapter 7, and of course anything that comes from the quizzes. So be sure to spend some time on the quizzes up to section 7.4, so that you can you're not caught off guard by those. Okay. I'll give a few more minutes for any questions, and then if the parents aren't anymore, then we can close up shop for Okay, let's call it a day. Of course, I'll stick around until everyone's gone. Well, here and online. And we'll cover the last midterm relevant section on Tuesday. You take each homework's coming, whatever homeworks have come in since last weekend will be graded this week.